This lecture will cover the CFA Level I reading on sampling and estimation. So let's start with the definition of a sample. A sample is defined as a subset of the population of interest. Let's say that our population of interest is represented by this large circle, and the population that we are concerned with is the return on 1 million stocks. So we have 1 million stocks. We are talking about the return of these stocks yesterday. So let's say that this represents all the stocks, all the publicly traded stocks in the world, and the returns are 1% minus 0.5%, etc. So we have a million such returns, and let's say that you want to find the average, denoted by mu, the average or the mean of these returns. It will be extremely time consuming to calculate the average returns for a million stocks. So what you might do is pull out a sample. So you can possibly create a sample with n equal to 100. This means that out of this whole large population of a million, you pull out 100 shares, and in that sample you might have returns like 1%, 2%, minus 1%, etc. So basically you will have 100 data points. Now finding the mean of the sample will be much easier. That mean is denoted by x bar, and it's clearly much easier to find the sample of the mean relative to finding the sample of the whole population. More importantly, if we want to estimate the population mean, one way of doing it is to take out the sample, calculate the sample mean denoted by x bar, and this is our approximation or our way of estimating the population mean. So as we said, a sample is this subset. Sampling is the process of obtaining this particular sample. Now there are different ways of sampling. One is called simple random sampling, where we randomly select 100 stocks from around the world. The issue with this might be that you might select all your stocks from Asia, and that might not be representative, because let's say that 50% of the market capitalization of the world is represented by US stocks, and if you don't have any US stocks in here, then there is a slight issue with our sample. So to deal with that problem, what we might do is stratified random sampling. In stratified random sampling, what you will do is take your population, and you might create strata or groups in your population. So you might basically divide your stocks into US stocks, Europe stocks, and Asia stocks. And if you say that 40 or 50% of the world's market capitalization is in the US, then in your sample of 100 you might pick 50 stocks from the US. If Europe represents 30% of the market capitalization, then you would pick 30 stocks from Europe and 20 stocks from Asia to make up your sample of 100. So by doing stratified random sampling, you create these three strata and pick the appropriate number of stocks or data points from each strata. Systematic random sampling is simply saying that if you have 1 million shares and you want to pick 100, then you organize these million shares in some sequence, and you simply pick every 10,000th share. So pick the first one, then the 10,000th one, and so on. So you ultimately have a sample of 100. So this is a bit like simple random sampling, but just done in a more systematic way. However, the issue will still remain that this has potentially the same issue as simple random sampling. A parameter is used to describe a population of data. So this is just terminology. When you are describing the population, so if you want to talk about the population mean, this is a parameter, or the population standard deviation, these are referred to as parameters. So when you are describing a population, what is used is a parameter. When you are describing a sample mean or sample standard deviation denoted by S, these are called statistics or sample statistics. Time series versus cross-sectional data. Time series is a sample of observations taken at specific and equally spaced points in time. So the monthly returns on Microsoft stock from January 1995 to January 2005 would be an example of time series data. Cross-sectional data is a sample of observations taken at a single point in time. So the sample of reported earnings per share of all NASDAQ companies for 2005 would be cross-sectional data. Sampling error is the difference between a sample statistic, such as the mean, variance, or standard deviation of the sample, and its corresponding population parameter. The sampling error of the mean would be the sample mean minus the population mean. So going back to the example we were just talking about, so let's say this is your population, and as we said earlier, we let's say have 1 million shares in our population, and let's say that if there was a way of finding the mean of the return for these million shares, let's say that the mean return was 2%, and when we pick out a sample of 100, n equals to 100, and we find the mean for this sample, let's say that that mean turns out to be 2.5. The sampling error of the mean then would be the sample mean, which is 2.5, minus the population mean, which is 2. So this gives us 0.5. What is sampling distribution? The sampling distribution of the sample statistic is the probability distribution of possible sample statistics computed from samples of the same size randomly drawn from the same population along with their associated probabilities. So let's just understand this with an illustration. Going back to our example where we have a population with 1 million stocks. If you draw a sample of n equals to 100, this population will have this sample will have a certain mean. So the population mean, let's say first is 2.5. Then you draw another sample again with n equal to 100. So this is your second sample. This might have a sample mean of 1.5, and you keep doing this. So draw several samples. What you will notice is there is a certain distribution for the sample mean. So you will have numbers like 2.5, 2.0, 1.5, etc., etc., etc. So clearly there is a distribution of the sample means. So the sample distribution, the sampling distribution simply refers to the distribution of these numbers. If we are in our example, we are simply taking the mean. We could easily be looking at the distribution of the standard deviations or the variance, but let's keep things simple and focus on the means. So this distribution is called the sampling distribution of the sample statistic. So the central limit theorem deals with the sample distribution of the sample means, which we were just talking about. And the central limit theorem, which is extremely important, says that for a population with mean mu and variance sigma squared, the sampling distribution of the sample means of all possible samples of size n will be approximately normally distributed, with a mean equal to mu and a variance equal to sigma squared over n. So continuing with our example, if this is our population and the same population of 1,000,000 stocks, let's say that this population has mean mu and standard deviation equal to sigma. What this is saying is that for the distribution of x bar, which is basically the many samples that we draw with n equal to 100, so the distribution of x bar, what will that look like? According to the central limit theorem, the expected value of x bar, so the expected value of the sample means is equal to mu, which is the population mean. So this is one aspect of the central limit theorem. The variance, so the variance of x bar is going to be equal to sigma squared. This is the variance of the population divided by n, which is the sample size. Now so this is point number 1, this is point number 2, and point number 3 is that this distribution of x bar will be normal. So we will have a normal distribution for x bar. In other words, the distribution of x bar will look something like this. So we'll have a normal distribution with mean equal to mu and sigma, actually this is referred to as S, the standard deviation of x bar will be equal to sigma divided by root n. This is simply the square root of this entity over here. So this is the central limit theorem. The standard error of the sample mean is the standard deviation of the distribution of the sample means. So this is just a definition that we just talked about. The whole point here is when we create a distribution of the sample mean, so this distribution is the distribution for the sample means. The standard deviation of the so this is sigma x. So sigma x is the standard deviation of the sample means is equal to sigma, which is the standard deviation of the population, divided by square root of n, which is the size of the sample. This works when the standard deviation of the population is known. Then obviously we use this formula. Then the standard error of the sample mean, which is denoted by this entity, is equal to sigma over root n. Let's do a simple example. If the mean stock price is 15 with a population standard deviation of $3, so let's say you are looking at 1,000,000 stocks and the mean stock price is 15, population standard deviation is 3. What's the standard error of the sample mean? So the standard error of the sample mean, denoted by this, is equal to sigma, which is the standard deviation of the population, divided by square root of n. The standard deviation of the population is given as 3, divided by square root of n, which is square root of 36. So we have 3 over 6, which is equal to 0.5. So this is the standard error of the sample mean. A similar example, a sample contains past 36 monthly returns. The mean return is 2% and the sample standard deviation is 10%. So notice here that the data we have now is a sample standard deviation. We don't have the standard deviation of the population. Calculate the standard error of the sample mean. So now if we don't have the population standard deviation, we simply use the sample standard deviation. So the sample standard deviation, so the way this will work is instead of using sigma for the population, we simply use the sample statistic, which is S, divided by root n. So the formula is fundamentally the same. S is the sample standard deviation, which is 10%, divided by root n. N is 36, so root n is 36, and we have 10 over 6, which is basically 1 and 4/6. Point estimates are single sample values used to estimate population parameters. The formula used to compute the point estimate is called the estimator. So, continuing with the example we are talking about, if we have this large population of 1 million stocks and we pull out a sample of 100, the estimate of the population mean can be obtained by taking the average or the mean of the sample. So if this mean is x hat, that is our point estimate. So x bar is the point estimate of the population mean. Now how do we come up with x bar? So that's this formula. So x bar is the summation of I equals 1 to n. So if n is 100, I is equal to 1 to 100 of xi, the whole thing divided by n. So this is simply a fancy way of writing the mean of all these 100 values. The value we obtain from this calculation for a specific sample is the point estimate of the mean. Properties of an estimator. 3 main properties. Number 1, unbiased. So with an unbiased estimator, the expected value of the estimator is equal to the parameter we are trying to estimate. In other words, when we draw this sample from the population, the expected value of x bar over here should be equal to the population mean. So if this is the case, then we say that we have an unbiased estimator. For example, the sample mean here is an unbiased estimator of the population mean. Number 2, efficient estimator. This is where the variance of the sampling distribution is smaller than all other unbiased estimators. So as an example, mode and median might be other unbiased estimators, but the variance of the sample mean is less than the variance of the other estimators, making the sample mean the most efficient estimator. The thing that you need to basically remember is efficient estimator means that the variance is the lowest relative to other estimators, other unbiased estimators. And finally, an estimator should be consistent, which means that the probability that estimate is close to the value of the population parameter increases as sample size increases. Now let's talk about the concept of confidence interval. We've seen this briefly in the previous lectures, but nevertheless, a confidence interval is a range for which one can assert with a given probability of 1 minus alpha that it will contain the parameter it is intended to estimate. 1 minus alpha is called the degree of confidence. Alpha is the significance level of the test, sometimes referred to rather confusingly as the confidence level. Let's take an example. The population mean will range from 15 to 20 with a 95% degree of confidence, or at the 5% significance level. So the way we look at this is as follows. Going back to our example, we have our population with a million values, and then we draw a sample from this with n equals to 100, and let's say that we come up with x bar is equal to 20. So x bar is 20. This is our estimate of what the population mean is. But can we say with 100% confidence that the population mean is 20? We cannot. Can we say with 90% confidence or 95% confidence? And the way that works is, we can say with 95% confidence, for example, that the population mean is within some range. So in the example given over here, we can say with 95% confidence that the population mean is between 15 and 25. So given that our sample mean was 20, based on that we can make a statement about the population mean being in this range. If you look at the probability distribution, essentially what we mean is, when we talk about a 95, the horizontal axis here is the possible values of the population mean. So if we are talking about 95% confidence level, then alpha is 5%. So 5% is the significance level, 95% is the confidence level. What we are basically saying here is that if we cover 95% of the area, this mean will be 20, and we can say with 95% confidence that the mean will be between 15 and 25. So this is the concept of the confidence interval. Now, how do we construct the confidence interval? Basically, the confidence interval is a point estimate plus minus a reliability factor times a standard error. The simple way of looking at it is, continuing with our example from before, if you are trying to gauge the mean for your population, and to do that you pull one sample, and in that sample say n is 100, and your x hat in that sample turns out to be 15. So the 15 is your point estimate. Now clearly you have to, as in you can't be 100% sure that the population mean is 15%, so you give a range. The range will be 15% plus or minus a number. Now how do you come up with this plus or minus the range basically? So we know that it's 15 plus or minus a certain amount. How do we figure out what that certain amount is? That certain amount is basically the reliability factor times the standard error. The reliability factor is based on the confidence interval. If you want to state this range with high confidence, let's say you want to be able to state with 99% confidence, then the reliability factor will be high. So you will need a larger number. On the other hand, if you are stating with only 90% confidence, then your reliability factor is lower, and this range can be a little lower. The other term that's relevant is the standard error of the point estimate that we've talked about earlier. The higher the standard error, the greater this range. Let's look at confidence interval in the context of a normal distribution. If the population you are dealing with has a normal distribution with a known variance, the confidence interval for the population mean can be established by using the z-score table, or basically a standard normal distribution. In this case, the confidence interval becomes our point estimate plus or minus, this is our reliability factor z alpha over 2 times the standard error, which is sigma, standard deviation of the population, divided by the square root of our square root of n, which is the sample size. This, if you recall, is our standard error. Now what's the interpretation of this? the interpretation of Z alpha over 2 is as follows. If alpha is equal to 10%, this means that our confidence level is 90%. And the way we look at this is, so if we have a normal distribution, alpha is equal to 10% means we have 5% in the tails and 90% in this area. So what we can then do is look at our probability tables, normal tables, and figure out this value and this value. These values we will call Z alpha over 2 and Z alpha over 2. So these are our reliability factors. The standard error is simply based on the standard deviation of the population divided by the sample size. Look at this example now. From a normal distribution with known variance, construct a 95% confidence interval for the population mean given a sample size of 100, standard deviation of 20 and sample mean of 15. So let's write our formula again. So our confidence interval is the point estimate plus or minus our Z alpha over 2 times sigma over square root of n. So our point estimate is x bar, which is 15, plus or minus Z alpha over 2. How do we find this? Given a 95% confidence interval, so this means that you have your normal distribution. 95% confidence interval means that we have 95% of the area over here, which means 2.5% here and 2.5% here. So this Z value is minus 2 approximately. It's 1.96 to be more precise, but let's just work with plus and minus 2. So you can look this up in your normal distribution tables, which we've studied in the previous lecture. So Z alpha over 2 is 2 and sigma is given, that is 20, divided by square root of n, which is square root of 100. So 2 times 20 over 10, 2 times 2 is 4. So basically we have 15 plus or minus 4. Essentially then what we are saying is that with 95% confidence we can say that the population mean is between 11 and 19. So that's one example. Now what are some standard reliability factors with a 90% confidence interval? Z alpha over 2 is 0.05 and our reliability factor is 1.65, and I'll strongly encourage you to memorize this information. All we are saying, you can look it up in the tables, but if you know this by heart, that just makes life easier. So 90% confidence means 90% here, 5% in each one of the tails, and this will correspond to a Z value of minus 1.65 and plus 1.65. With a 95% confidence, we have more area under the curve, so the Z values become larger, 1.96 plus or minus to be exact, but this is approximately equal to 2. 99% confidence further increases the Z value to 2.58 or approximately 2.6. Notice that 1 minus alpha confidence interval, so the 90% corresponds to 1 minus alpha, so the reliability factor is for Z alpha over 2, which is alpha becomes 10%, alpha over 2 is 5%. That's where the alpha over 2 comes from. Students' T distribution. The Z distribution that we've been talking about so far works well when the population variance is known and or the sample size is large. By large we mean sample size greater than 30. If these conditions don't hold, which means that your variance is unknown, and you are dealing with a small sample size, then use the t distribution. The t distribution is less peaked than a normal distribution with more probability in the tails. As the degrees of freedom, so the degrees of freedom is basically equal to the sample size minus 1. So as the degrees of freedom gets larger, the shape of the t distribution approaches a standard normal. So when degrees of freedom is relatively large, let's say 100, the shape of the t distribution will essentially be like a normal distribution. How do we read a t distribution? Basically, you now have to worry about degrees of freedom also, which is equal to the sample size minus 1. And the interpretation, again, the general shape of the t distribution is like this. So let's say that you take a sample size of 20. So if n is equal to 20, then the degrees of freedom will be 19. And let's say that you want to determine the t distribution for a probability of 0.05. The way this works is the way it's given over here. So let's say distribution of 0.05. We are doing what's called a one-tail test here, which means that we are assuming that the entire probability, the subscript over here, is in the right tail, 0.05. Remember, these are centered at 0. So like our standard normal distribution, this is also centered at 0. And what this number basically says is that if we have 0.05 in the right tail, then for degrees of freedom equal to 19, the value over here, the t 0.05 is 1.73. Notice that if you have less probability in the tails, like you have over here 0.025, then the t value becomes larger and larger. So as we have less and less probability in the tails, the value of the t value increases. The t distribution is used to construct the confidence interval if the population has a normal distribution with an unknown variance. So we've already talked about that. Construction of the confidence interval is exactly like what we've seen before. The only difference is that instead of z alpha over 2, we now use t alpha over 2, and instead of using the population standard deviation, we are using the sample standard deviation. Let's talk about some possible biases when dealing with data. A common bias is a data mining bias. To understanding data mining bias, first let's just understand data mining. So data mining occurs when analysts repeatedly use the same database to search for patterns or trading rules until one that works is discovered. So this implies that clearly if you've tried several patterns, the one that you think works might just be a chance. So for example, empirical research has provided evidence that value stocks appear to outperform growth stocks. Now this could be a coincidence if you have tried several combinations and based on the data this just turns out to be true. Now what's the data mining bias? This refers to results where the statistical significance of the pattern is overestimated because the results were found through data mining. What are some warning signs for the existence of data mining bias? And from an exam perspective, this is what you need to keep an eye on. Number 1, trying many variables before stumbling on one that appears significant. And number 2, if there is no logical explanation for what the data mining results are giving you. Some other biases. Sample selection bias occurs when some data is systematically excluded from the analysis, usually because of the lack of availability. A common example of this is survivorship bias, where if you study mutual fund returns over the last 5 years and you only look at the survivors, so you only look at the funds that have survived, and essentially you are not looking at the funds that did not survive. So this would result in a sample selection bias, and the specific type of sample selection bias here is called the survivorship bias. You will see this again later in the course. A look-ahead bias occurs when a study tests a relationship using sample data that was not available on the test date. So for example, if you are looking at a test that deals with price divided by book value, and the book value numbers that you are using are from the end of the last fiscal year, but price is based on current prices, so such data will have look-ahead bias. Finally, time period bias results. There might be a time period bias if the results are time period specific. For example, if time period is short, the data under study may reflect phenomena specific to that period. For example, if you are predicting or measuring EPS numbers and you only take Karachi Stock Exchange data for the last 1 year, the situation or the economic situation in the last 1 year has not been representative of the last 10 years, for example, and hence if you just use 1 year's worth of data, then there might be a time period bias, so bias towards whatever happened in the last year. Similarly, if the time period is too long, then fundamental structural changes may have occurred which impacts the data that we are studying. Here, for example, if you are looking at American stock data from 1900 to 2011, and here again there might be a time period bias, because let's say that since 1960s there's been a structural change in the economy, and if we are taking data since 1900, then the fact that this is the relevant structure of the economy, that will be diluted by also taking data that is very old. So bottom line is, you might have time period bias if your data period is too short or if the time period is too long.